Welcome also from my side. Good morning from Germany and good afternoon to India. So I want to talk about the study we have done in the last couple of months, 1 year approximately, about grid support services from solar rooftop PV systems and storage. And the next around about 20 minutes, this is the agenda. I want to talk about the challenges we are seeing, but also the services and more general. And the main content will be a case study we have performed for BRPL, both on the distribution transformer level. We had a very nice introduction of Abhishek for now, at the DISCOM level, and then also giving an overview of the economic analysis, and finally then the conclusion and recommendations. So let's have a look at the challenges and services from rooftop PV and batteries. And of course, we have to look at the rooftop PV first. So for DISCOMs, there are a couple of challenges we see. Just get this away. It's disturbing. Okay, that's better. And we've heard about that yesterday already. So there's the issues of uploading different load patterns we are seeing, and it has an impact on voltage. Frequency control will be more difficult in future, for sure, having the large variations of solar power. Then a question of protection and also reverse power flow. This is actually it does provide issues, and mainly also what I talked about yesterday, overloading of assets, especially the lines, transformers, the cables, and so on. So this is definitely on one side where we have the challenges. On the other hand, we also can receive services, both from PV systems themselves, but also from batteries. So we talk about the load patterns. Yes, the load pattern will change, but also the load peak will be reduced. It was mentioned earlier in the previous presentation that the day peak is reduced by the PV systems, and yes, also the night peak can be reduced, and for example, by batteries. With regard to voltage and frequency control, we can have frequency regulation, especially from batteries, but also frequency support from PV systems, and also receive voltage support. I've shown this yesterday also with regard to the power provision from PV systems, according to a power factor, or maybe more advanced with the load bar. On one hand, we have the protection of reverse power flow. On the other hand, we have also as a service increased self-consumption, so the overall consumption will be reduced. The grid will be actually then relieved. So, for example, peak shaving of solar PV can be done by batteries. And with regard to the overloading of assets, actually, we also see some benefits from solar, reducing the daily peak, for example, but also using the batteries, for example, to reduce, again, the loading on the transformer, on the lines, and therefore also have an upgrade deferral. So, if we don't start on the different services which are out there, they are almost infinite. There are so many use cases, possibilities, so this can only be a small fraction I'm showing you currently here. Part of this was also mentioned in the previous presentation already, like frequencies support. We have the reactive power provision, voltage control. We look at the larger utility batteries, for example. We can go into black starting. We can support black starting or island operation. We can use the batteries for ramp rate control, for balancing support services, but also many parts of the world is used fast frequency regulation, like primary reserve, or even faster than primary reserve, or using it as energy shifting. Then for looking at PV itself only, we can reduce the losses on in the distribution system, because consumption and production is closer together, so therefore there are less losses. We will have a look at this later on as well. And especially for India, there's a contribution to the RPOs, to the purchase obligations. and more behind the meter. Of course, energy shifting is also possible, and also to reduce PV curtailment, especially in case, for example, you have a large PV system and the grid connection is smaller, and in combination with battery, for example, to reduce. So we have looked at much more, but we have then decided for the specific project to look more detail into a couple of these services, and this is basically the final list we have then chosen, and we divide it into the distribution transformer level and into the DISCOM level. It was previously called also grid level or power system level, and here to get a better understanding what we are seeing from an economic point of view, what is the value for DISCOMs, like we talk about load reduction, which can be provided by PV during the day, I mentioned that, or by batteries in the evening. Also, we can then reduce the loading on the assets, especially on the transformer, therefore have a couple of years more lifetime of the transformer, but can also avoid power purchase agreement costs. Further, if we have a large amount of PV in the system, I've shown this yesterday, then we can use batteries for the PV reduction. Therefore, again, we don't have to upgrade the transformer. We have also an upgrade at deferrals, so also some advantages there. Then on the reactive power side, we can provide voltage support, both to improve its voltage situation in the grid. This can be both provided by PV, reactive power, but also by battery, both as active and reactive power. But also, if you talk about the providing reactive power to consumers next by or to the overloading level, then this can also be provided by PV and or batteries, for example, to avoid reactive power balance penalties. Finally, on the DT level, we do have the reduction of the losses. I don't really want to have the batteries involved in here. The main reason for that is that batteries also produce some losses. So here, definitely see the advantage from the PV system themselves having the PV system located very close to the load itself. On a DISCOM level, we have identified balancing as a grid support service. So there's a deviation settlement mechanism charges currently there. And therefore, if forecasting and the actual demand is not matching well, a battery is very well suited to actually provide a better match and do a balancing, further energy shifting, avoid power purchase agreements, and then on the PV system side, power demand reduction by PV, so KPA, variable cost, and also mentioned distribution to DISCOMs RPO. So let's have a look now a bit more in detail into the different grid support services and what we have analyzed so far. Let's start with the distribution transformer level analysis, and we look into an 11 kV feeder. It's an urban area, around about 3,000 consumers, mainly residential consumers, and in there are 5 distribution transformers. Each of them has 990 kVA, around about 1 megawatt volt ampere, and range from 11 kV down to 400 kV. On the right-hand side, you can see the total power consumption on these of the 11 kV feeders from 2017, 18, and 19. And you can see that there is an increase. And basically, we are doing our simulations, our modeling, forward-looking. Therefore, we increased, and also according to this, around about 5% per year. The load on these feeders, actually also depending on the season. So, for example, you can see during winter time the increase is not as high as during summertime. This is most likely mainly also to using more and more air conditioning on that already. So let's have a look at the first results about reduction of overloading by PV and batteries. On the upper picture, you can see a week, not quite a week, 5 days of load. Basically, there's the transformer capacity at 1 MVA, and we can see that there are certain times here and here, basically, where there was overloading, and now having PV in there, we assume a PV share of 50% in this case, so connected to the transformers or rated to the transformers, then we can see that the peaks during the midday, like this one, this one, so the gray is the original one, the blue one is the new characteristic having PV in there, but it actually reduced quite considerably the loading and the loading on the transformer. So that definitely gives benefits. How would we operate a battery? How could be a battery operated? You can see that down here. So we have a small battery connect, 100 kW is 4 kilowatt hours approximately. And you can see again here as a peak shifting situation, and again shading the peaks during when it's overloading of the transformer, and then recharging as soon as we're getting into the safe area. So that's what we have done for a complete year, both for PV, both for batteries, for a combination of those, and also then for different sizes. And let's have a look at the result. So if we are now increasing basically the amount of share of batteries in PV, so this is from 0 PV and battery towards 100%, and separating between PV only, so blue line, battery only, that's the orange line, and the combination of those, that's the green line. We can see that we can actually increase the lifetime by up to 4 years when having PV in there, and we can actually have a pretty high share already by using PV only. Obviously, the impact of PV is not as high as from batteries. The main reason for that is, of course, that we are pretty much depends how well the load and the PV production is correlated, whereas with battery we can obviously then control very nicely. Let's jump to the next topic, reduction of transformer loading caused by PV. So now we are in the reversed flow situation. We can see that we are now in a negative area. So we assumed a very low loading feeder with a very high share of PV, and then we add the battery. And there we can see that here the peak shaving of the battery is happening here, basically providing towards the load here, and so on. So again, if we have a very high share of PV with a very high reverse flow, which would then lead to overloading of the transformers, then we can also reduce this by using a battery for PV peak shaving. And the results for that, even we identified a transformer lifetime increase of 12 years, so that's even a very high impact, and that's like I mentioned yesterday, batteries in combination with PV does really help to increase the hosting capacity, or in this case also to increase the transformer lifetime. Let's go to the next one, which is the voltage support. We had looked into two control modes, into a constant power factor of 0.95 inductive typically, so it's drawing reactive power. Main reason for that is that if you have a high voltage and try to reduce the voltage, so you're not going up limit PV. And on the other hand, the volt bar characteristic, or sometimes QE characteristic, which is only used then if there is really an issue on the voltage. So this is a typical characteristic. So the higher the voltage is, start trying to use the voltage. If there's a low voltage situation, trying to push the voltage basically to get a nicer voltage profile. So this is then the result. Also, again, depending on the share of photovoltaic, in this case, we here 150%. And what you can see here is the maximum loading on the lines, basically, where we do see that with an inductive operation, we have then a large increase. That's because of the high reactive power. The loading of this line or of this transformer was actually quite high already in the very beginning. So without PV, so it's already 100% actually. So and what's more important now for the first part is that voltage here, that's the maximum voltage we're seeing, and the minimum voltage we are seeing, that basically the QV characteristic, which is the blue line, the volt bar, is actually supporting very nicely then also in the low voltage situation, so increasing the voltage there basically, and at the same time reducing the loading, so helping basically also to reduce the situation. So from this we can conclude that volt-var characteristic is definitely a very good option to be used in inverters for reactive power control. Let's have a look at the next one, which is the reactive power provision for the overlaying grid. And here you can see that we have increased the power PV generation from 0 to 100%, which is around about 5 megawatt in this whole distribution system we have analyzed. And we then had a look at, okay, what can the PV system themselves provide? That's the red dots. Each dot actually represents 1 hour in a year. So that's the red dots basically in one direction. So capacitive, so receiving reactive power. And on the other hand, the dark blue line, which is a bit hidden here, but you can see it here much nicer, is then in the opposite direction. And this is the typical range we have identified. Inverter, also inverters in India, used in India, can actually provide. Many grid codes also require that. Often it's even more than that, but that's kind of the minimum requirement. And compared to what I have heard in the poll, we believe that inverters use a large server actually, that the inverters in India also are pretty much capable of providing quite a number of services. Yeah, of course there are some limits for sure. So what we can see here is that if you have a large amount, and then yes, so that's the dark one is what is actually provided by the PV system, and then the orange one is what is actually received or can be then provided to the overlaying grid. And why is that not identical and why is it scattered? Well, the main reason for that is, of course, what is the current loading situation in the grid and what are the assets themselves actually provide or consuming. So the transformer, the lines, and so on, which of course also have an impact on the reactive power. And that's the main reason why it is actually then pushed to the top here with regard to reactive power. That's the main reason for that. And secondly, of course, depending on the current loading situation. What we can see is that as soon as we have a large amount of PV in the system, that we are getting a gray area, which we can call a controllable area. So we're able to give set points to the different inverters, basically provide about a certain amount of reactive power, then we can control the reactive power provision at the overlaying grid. And this is especially very interesting for a future power system when reactive power becomes even more important than today in order to keep even the voltage and the reactive power balances in the correct manner. And in many countries, there are also already penalties if you're not keeping your reactive power at a certain level. So we believe controllability of large PV system is necessary, and this basically allows to provide power the wide range to the overlaying. And finally, on the detail level, I want to talk about the grid losses. Already mentioned that this is very much related to PV, not so much to batteries, as they have their own losses. And what we can see here when analyzing this, again, increasing the share, we can reduce the losses in the grid up to like around about 40 or 50%. So why that? Because that's in the range where load and generation comes well together, and therefore the transport of the amount of electricity is actually reduced, and therefore also the losses are reduced. As soon as we are switching into a more reverse flow situation, which is happening after 50 or 60% basically, then the losses will actually increase, but they will only increase above 80% then if we compare it to what they were in the very beginning. And now keeping in mind that typical penetration rates, we are safe, 70-75% mentioned by Europe, so we definitely will always be better than what we have before. Including PV will also give will give benefits for the discom, because then the losses will definitely be reduced. Now going to the discom level analysis, so more on the distribution transformer, but below discom. And there we look into the balancing first. So here you can see a typical days, actually it's typical day characteristic of the consumption. And what is shown here is basically the projection of the load compared then to how the actual consumption has happened. And therefore, then if there's a mismatch, there's a deviation, then deviation settlement mechanisms are happening nowadays in India. And what we have done is basically we have the 20 megawatt hour battery and how this could be operated. See charging, discharging activities, especially there where the penalties are extremely high. High penalties are typically there where the mismatch is high, and also the frequency is also at a very poor stage, so out of nominal. We have identified with a 20 megawatt hour battery that you save per year around about 37 million. Further, we have looked into the energy shifting. So the question would typically, if you have power purchase agreements, then you have some agreements which are quite nicely, which are cheaper and have a very high load situation. You either have to go to the market to get the electricity quite expensive, or you have your more expensive power plant. So typically what you try is you try to cap the peak shave the high load situation in order to save on the PPA costs, and then you're using the more cheaper situations for then charging the batteries. So this is very typical that you then have like 1 or 2 cycles per day. So charging is here, discharging here. Identified as a 20 megawatt hour battery that can save 3.5 million rupees. We have looked into many, many more. I cannot show this here because of limited time, but please have a look at our report, which will be published soon. I just want to give you an economic overview of our analysis so far, and I've chosen 4 grid support services for this, especially combination with battery. First one is the load peak reduction, which basically allowed us, as we have seen, a saving of 4 years fixed deferral. Then we have the PV peak reduction, which allowed for 12 years actually. Then the balancing frequency regulation or balancing part, which is savings on the settlement mechanisms, and finally the energy shift. We do all the calculation for the specific year and the lifetime of the battery is 15 years. We do find that the net present sum is always negative. So from this we can conclude that there is actually many use cases I have shown to you, but we did not really identify any business cases as today. So from this, we need to conclude that there are incentives required in order to push this forward. And with this, I want to finalize my presentation with a conclusion and recommendations. Let's focus first on the rooftop PV or the PV in general. We believe that the inverters are currently used in India. Most of them are pretty well actually on providing services. So, for example, the voltage support capability is possible. Also, frequency sensitive mode, which basically means if the frequency goes up, then that basically means that the power is too high in the overall system, that they would actually reduce their power output. So that of course is true. So this should be required from all PV systems. It's international good practice, and it is available, like what we have seen so far. And of course, I have shown to you that the volt-var characteristic is quite good. On the other hand, we believe it should be up to the discom itself to choose which kind of power control to be used. Because in some systems or distribution system where there's a low penetration, for example, you might just want to continue operate this power factor 1, because you don't want to have any interference with the inverter itself, or you don't want to have any additional power. On the other hand, you want to have support also might be a choice or a constant power. For frequency and voltage support coordination, we definitely need also coordination with the transmission system. So especially frequency is something like this, something is very much linked to the whole power system. For large PV plants, we recommend to have a control of active dose and active and reactive power, should also be implemented which codes there, and I've shown the example where and you can have control of the team to provide reactive power to globally with A and I guess looks like we are facing some audio problems from the feed coming from Dr. Foster. So Dr. Foster, if you are able to hear us, actually there is some internet issues from your side because the feed coming from you is getting blank. So can maybe once try to reconnect and